Hey you guys, today we're going to be talking about section 3.1, acceleration. So acceleration is going to be the rate at which our velocity changes. And this can happen two times. Velocity can change in two situations. One is when the speed of an object changes, and the other one is actually when the direction changes, okay? Which makes sense, right? Because we've said velocity can either be positive or negative, right? And that those just mean direction. So of course, velocity is going to change when our speed changes, but it's also going to change when we change from going like left to right, okay? So acceleration is going to occur when either of those two things happen or when both happen at the same time. So let's say that our speed and our direction changes together. Let's look at an example though, okay? So we're on the road and we are going to go on our bicycle. When we start out, we are going to be at position x equals 0 meters, time equals 0 seconds, and velocity equals 0 meters per second, okay? Then we're gonna get a little bit of ways. We're gonna be right here now, okay? Now we are at x equals 1 meter, t equals 1 second, and our velocity is 2, okay? Velocity is going to be 2 meters per second. Then we're going to get a little bit further along. All right, now we're at x equals 4 meters. Now t equals 2 seconds, and our velocity is equal to 4 meters per second, okay? Finally, we are going to reach that our position is at 9 meters, our time is at 3 seconds, and now our velocity is all the way up to 6 meters per second. So what's happening here is that the cyclist is actually increasing their speed by 2 meters per second every second. See how we go from 0 to 2, from 2 to 4, and 4 to 6. So every second, they're going 2 meters per second faster than they were previously, okay? Now, another thing to consider with velocity and acceleration is just, do we feel velocity? So like when you're in your car, do you feel it going 60 miles per hour? Does your body feel different than you do when you go 20 miles per hour? Not really. But what about acceleration? Do you feel acceleration? That would be like if you or your friend slams on the brakes in their cars. If they slam on the brakes, what happens? You get jerked forward, right? Okay, that's because your acceleration has changed. You were going one direction, now the acceleration is acting against you, right? So it's pushing you back. The acceleration is pushing against you and you feel it. Now, if we're wondering, well, what does that look like mathematically? We're gonna have that our average acceleration is equal to a change in velocity over a change in time. And if you guys remember what we said about when we have these changes, we can represent them as our final velocity minus our initial velocity over our final time minus our initial time, okay? The units for acceleration, if we look at it, we have meters per second over seconds. So our units come out to meters per second squared. Meters per second squared is going to be our units for acceleration. So let's do some examples together, all right? First one, what's the acceleration? So we have an advertisement and it says that a car can go from 0 to 26.8 meters per second in 6.2 seconds. Okay. If that's what it's saying, we know our knowns are that our velocity initially is going to be 0 meters per second. And they're saying it's going to get up to 26.8 meters per second and a change in time of only 6.2 seconds. And we want to know what the average velocity, what the average acceleration is of this car. What is the average acceleration? Okay, so we just learned that average acceleration is equal to the change in velocity over the change in time, right? So we're going to have our final velocity minus our initial velocity divided by that change in time. If you type in 26.8 divided by 6.2 into your calculator, what do you get? I get 4.3 meters per second squared. That's what I get. I hope you got the same thing, okay? So now let's look at another example. We have a drag racer and he's gonna deploy a parachute. So he's gonna get so far, then he deploys a parachute to try and slow him down some. He's going to slow down from his initial velocity of 130 meters per second to a final velocity of 45 meters per second, and it's only going to take him a total time of 3 seconds to get there. And we want to know what is his average acceleration. So we're going to have to do final velocity minus that initial velocity divided by that change in time, all right? So when we do 45 minus 130 divided by 3, we are going to get a time of an acceleration of 28.3 meters per second squared. That is going to be our acceleration for the drag racer. You'll notice that it's negative. That's because our drag racer was going in the positive direction, and now he's getting slowed down, and it's working against him. So it's going in the opposite direction to slow him down. So that's why if we're going in a positive direction, our acceleration is now negative. So you can indeed have a negative acceleration. Okay, so to keep on going with the drag racers, but make it a little bit more interesting, we're gonna have one winning, okay? And the winner was traveling with a speed of 140.3 meters per second at the end of his quarter mile, okay? That is his final velocity. He started from rest and he was speeding up at an average acceleration of 30.4 meters per second squared. All right? What we want to know is what was his winning time for the race, okay? So this is what he started at. He started from rest. Then he raced all the way around. When he crossed the finish line, he was going 140.3 meters per second, and he had sped up 30.4 meters per second every single second, okay? So we want to find his time. If we look at our equation of the average velocity is equal to delta V over delta T, all right? And we break it up, and we get V final minus V initial over T final minus T initial. We're going to know that we're looking for that final speed. So he started out at T equals 0 with a velocity of 0 meters per second. So all we're going to have to do is solve for TF now. So we're going to have our average acceleration is now going to be equal to our final velocity over that final time. And remember, we're looking for that final time. So we're going to have our average acceleration times that final time is equal to our final velocity. And then finally, we'll divide both sides by that average acceleration to give us that our final time is equal to our final velocity divided by our average acceleration. Thankfully, we have the final velocity and we have our average acceleration, so we can plug them in. We're going to have 140.3 meters per second divided by 30.4 meters per second squared. Now plug that into your calculator. What do you get? Okay, I hope that you got 4.62 seconds. as your winning time. Your winning time should be 4.62 seconds. Okay, let's go on to another example. Today is full with examples because I know you guys need to see me work out as many problems as possible, okay? So this next example is about a chameleon's tongue. So he's going to extend his tongue to capture a tasty insect, all right? And the chameleon's tongue is going to accelerate at 33 meters per second squared for a time of 0.12 seconds to make the capture. We want to know the speed of the chameleon's tongue when it grabs the insect. So since it didn't give us an initial speed, we can assume that his tongue was starting from rest, okay? And what we want to find is the final velocity of his tongue when it's catching the insect. So again, we're going to have that our acceleration is equal to the change in velocity over the change in time. And we have that the change in velocity is VF minus V naught over TF minus T naught. We know that both of these are 0. So we're going to have our final velocity over our final time is equal to acceleration. And we're solving for this final velocity, right? So we're going to do acceleration times our time is equal to that final velocity. Our acceleration is 33 meters per second squared, and our time is 0.12 seconds. So when you do 33 meters per second squared times 0.12 seconds, you should get that his tongue was going at a velocity of 3.96 meters per second when he caught that insect. All right, now we're going to talk about how acceleration can be determined graphically, so with a graph. Because remember, we found velocity from a position graph, didn't we? We said that velocity is the slope of a position graph. So, interestingly enough, acceleration is the slope of a velocity graph. So, let's look at this graph right here. We're going to have a velocity versus time graph, okay? We're going to go from 0 to 5. So we're going to have 1, 2, 3, 4, 5. And then on our velocity, we're going to go from 1 to 3, okay? 1, 2, 3. Now, at 1 second, we're going to be at half a meter, then half meters per second. Then we're going to be at 1 meters per second, then 1.5, then 2 meters per second, then 2.5 meters per second, okay? And it gives us this nice linear distribution for the graph. So, since I said that acceleration is the slope of a velocity graph, that means that all we need to do is rise over run. So let's say we run from 2 to 3. That would mean we rise from 1 to 1.5. So our rise is our change in velocity and our run is our change in time. So when we do the rise over run, we're going to have that our change in velocity. All right, you guys, so we're going to do rise over run, okay? Our rise is our change in delta V, is our change in velocity. Our run is our change in t. So on our rise, we end at 1.5 and we started at 1. And then on our run, we end at 3 and we started at 2. So we're going to get 0.5 over 1, which means that our acceleration is 0.5 meters per second squared, okay? Because velocity versus time graphs, their slope gives us acceleration, all right? So a little test here, little quiz. Let's look at two lines on the same graph, okay? So this is our velocity versus time graph. We have line A, okay? And we have line B. We have line A, we have line B. I'm asking you right now at home, which line has the greater acceleration? Is it line A or is it line B? Okay, hopefully you answered line B. How do we know it's line B? Line B has a steeper slope than line A. We're having a bigger change in our velocity, which means it's going to give us a bigger acceleration. All right, that was just a little check so I could find out. Okay, next we have another example. So how much time to get up to speed? We have a subway train, okay? And it speeds up with an average acceleration of 1.2 meters per second squared. We want to know how much time it takes for the train's speed to increase by 4.1 meters per second, okay? So we want it to change in velocity by 4.1 meters per second because we want it to increase by that. So that's how much it's going to change. So what is our delta t? Well, we have acceleration is equal to delta v over delta t, and we're solving for delta t. We're going to multiply both sides by delta t to get a delta t equals delta v, and then divide both sides by a to get that delta t is equal to delta v over a, okay? Our delta v is 4.1 meters per second, and our a is 1.2 meters per second squared. So if we do 4.1 meters per second divided by 1.2 meters per second squared, what do we get? Okay, I got 3.4 seconds. I got that it's going to take 3.4 seconds for the train to increase its speed by 4.1 meters per second. I hope you guys got the same thing. Okay, now, since I know you guys love trains so much, I want to do another train problem. And what I'm referencing is, remember when we did that first problem set? All the problems with trains are what you guys wanted me to go over. Trains they can be hard, okay? So, as a train accelerates from a station, it reaches a speed, which means that's going to be its final speed, of 4.7 meters per second. And it reaches that speed in 5 seconds. So that means our delta t is going to be 5 seconds. If the train's acceleration is constant, what is its speed after an additional 6 seconds have passed? Okay, so that means we've gone 5 seconds, but an additional 6 seconds have passed. So that's going to mean that overall our delta t is going to end up being 11 seconds. But before we deal with that, we need to focus on finding what the acceleration is here, okay? When they don't tell us an initial time, an initial velocity, and it says that they started out from something, we're going to assume that v naught is equal to 0 meters per second. So that means that this is the total change in velocity, this is the total change in time. So we can do acceleration equals change in velocity over change in time, and we'll get 4.7 meters per second over 5 seconds. And when we do 4.7 meters per second divided by 5 seconds, we're going to get that the acceleration was 0.94 meters per second squared, okay? That's not the end though. What we want is we want to know what is the speed after an additional 6 seconds have passed. So it's going to be 11 seconds after it initially leaves, okay? We want to know what speed it is. So if we have that acceleration is equal to the change in velocity over the change in time, well, we want to solve for VF, right? So we're going to rearrange it. We're going to have A delta T is equal to VF minus V naught, which then will become A delta T plus V naught equals V final, all right? We started from rest, right, because we were leaving. So we're going to have A delta T equals VF. Our acceleration we just found is 0.94 meters per second squared. And our delta T is going to be 11 seconds because 5 plus 6 is 11. So if we do our acceleration times our change in time, we're going to get that our velocity at the end is equal to 10.34 meters per second. That's going to be our velocity after an additional 6 seconds has passed for a total of 11 seconds. But before we get to the ferry dogs, I want to explain one thing that's in your note PDF to you, okay? It talks about decelerating, okay? So all it means to decelerate is that you're going one way with your motion. So let's say you're going to the right. All deceleration would be is if your acceleration was acting the opposite to you, okay? So if you're going to the right, deceleration would be your acceleration acting to the left. So if you're walking to the left, which way would your deceleration be acting? It'd be acting to the right, okay? All it means is that it's going to be against the direction of motion, okay? Against the direction of motion. So if you're moving in a negative direction, a positive acceleration would be considered deceleration for you. But if you're moving in a positive direction, a negative acceleration would be deceleration for you. So just keep that in mind. Deceleration doesn't just have to do with the line. It has to do with going against your motion, okay? And then it has this graph. I don't want to have to draw it right now, okay? And it asks you which lines are slowing down and which ones are speeding up. So look at it for a second. Okay. The lines that are slowing down are 1, 2, and 4. And that's because if you look, they're all approaching 0 meters per second. The one speeding up is 3 because even though it's becoming a more negative velocity, that just means it's moving faster to the left. Okay. So let's talk about the ferry docks. So a ferry makes a short run between two docks. One in Anacortes, Washington, and the other in Guemes Island. So the ferry moves in a positive X direction as it approaches the island with a speed of 7.4 meters per second. Okay, so it's moving in a positive direction. So that means it's going to be a positive 7.4 meters per second, okay? The first thing we want to know is if the ferry slows to a stop in 12.3 seconds, what is its average acceleration? Okay? So we have that our average acceleration is equal to delta V over delta T. If it's going to a stop, its final velocity is going to be 0, and its initial velocity is going to be the 7.4 meters per second, divided by the time it takes it to stop, which is 12.3 seconds. So if you type that into your calculator, you should get that the acceleration is negative 0.60 meters per second squared. All right? So that answers part A. If the ferry slows to a stop in 12.3 seconds, what is the average acceleration? Part B says the ferry returns to the Anacortes dock with a speed of 7.3 meters per second. Okay? So our V naught is 7.3, but remember, it's returning now. So when it was heading to the island, it was going in the positive direction. Now it's been going in the negative direction, so 7.3 meters per second. And it comes to rest in 13.1 seconds, which means that its final velocity is going to be 0 meters per second. And we want to know what's the average acceleration of it now. Well, once again, we know that the acceleration is equal to delta V over delta T. We're stopping at 0, so it's going to be 0 minus negative 7.3 meters per second divided by 13.1 seconds, okay? When you type that into your calculator, you should get that the acceleration here is equal to 0.56 meters per second squared, okay? Now you might have noticed though, just one quick thing, that while I was doing this problem, the problem says speed, but I was writing the velocity, okay? Why I was doing that is because these problems deal with acceleration. So if it's an acceleration related problem, even if it says speed, it wants you to think in terms of velocity, because acceleration has to do with the change in velocity, not the change in speed. So keep that in mind when we're doing acceleration problems in class. Whether we say speed or velocity, what we really mean is velocity, all right? I hope you guys have all had a great day. I will see you in class soon.